Good morning. We present to your attention the results of research devoted to enhancement of the technology of caved ore drawing from the ore deposit footwall triangle. Krivi-Irig iron ore deposit is a narrow strip of metamorphic rocks, and it is an integral part of Krivi-Irig Peremetchyk deposit extending from south to north. The length of the ore deposits along the strike varies from 0.8 to 2.5 kilometers due to different mining and geological conditions at different enterprises. Krivi-Irig deposit consists of 4 suites: schist amphibolite, K0, lower arkosephyllite, K1, middle iron ore, K2, upper schist, K3, ones. The main productive thickness is K2, which embraces 7 pairs of interchanging ore and schist layers. The underground mines are working out the 4th, 5th, and 6th ferruginous levels with rich iron ores. The average iron content is 60 to 63%, represented by various forms: stratal, layer-shaped, lenticular, pillar-like, and nested, and in some cases their combinations within a mining block. Rocks of the hanging wall and footwall are represented by strong, stable martite hornfells with ultimate compression strength of 100 to 130 megapascals and goethite hematite martite hornfells with ultimate compression strength of 70 to 90 megapascals. Physical properties of rocks are given in table. As is seen from table, physical and mechanical properties of the rocks are wide in range. When mining iron ore, over 60% of underground mines of Krivi-Irig iron ore basin apply a system with the bulk caving of ore and overlying rocks. These mining systems have the following disadvantages: ore losses on the footwall, up to 30 to 50% of the total ore losses; ore dilution, by 3 to 5% more than standard; reduced content of the useful component in the mined ore mass. When the deposit dip is 45 to 60 degrees, application of these mining systems results in about 30 to 40% of ore lost on the footwall. Increased losses of ore during mining lead to an increase in the specific volume of mining and capital works, preterm mining of levels. In this regard, the scientific and technical task of studying and enhancing the technology of mining ore deposits by the underground method for Krivi-Irig iron ore basin in the triangle of the footwall, in the dead area, when working out ore deposits with a dip of 45 to 60 degrees to minimize ore losses, is topical. One of the solutions for this scientific and technical problem involves developing a method to reduce ore losses in the footwall triangle without increasing the cost of caved ore drawing. The present work aims to study and enhance the technology of mining ore deposits by enhancing the mode of drawing, which will reduce ore losses on the footwall in underground mining at Krivi-Irig iron ore basin. To achieve this goal, it is necessary to solve the following tasks. Caved ore drawing from blocks when using systems with the bulk caving of ore is one of the most important production processes. Depending on the accepted method of ore drawing, ore losses and dilution are calculated, and the main parameters of the mining system are determined. This is due to the fact that 30 to 45% of the caved ore reserves is drawn from a block under overlying rocks, while losses in the block make 14 to 16%, and ore dilution is 12 to 20%. A significant number of publications are devoted to the issue of reducing losses and dilution of caved ore from the stoping block. Scientists of Krivi-Irig National University, Ukraine, have made a significant contribution concerning ore drawing under caved rocks. The panel enclosed by vertical walls of the ore massif from 4 sides is more favorable in terms of drawing from blocks, as such conditions increase extraction indicators. To reduce ore losses on the footwall when mining deposits with a dip of less than 60 degrees, the following technological solutions are applied. A significant contribution to development of the theory of ore drawing has been made by Malakhov, Kulikov, Terpogasov, Imanitov, Korj, and others. According to the results of their research, it is established that when caved ore is drawn from the mining block, the following figures are formed: ellipsoid of drawing, ellipsoid of loosening, and draw crater. The volume of the ellipsoid of loosening QL is about 15 times larger than that of the ellipsoid of drawing for loose non-compacted materials. Therefore, the volume of the ellipsoid of loosening can be determined by the expression Knowing the ratio of the volume of the ellipsoid of loosening to that of drawing, the latter can be determined according to the expression. Laboratory studies enable establishing that the figure of drawing changes depending on the surface inclination angle. The results of studying changes in or drawing angles depending on the surface inclination, distances between the draw point and the inclined surface and the width of the caved layer in the lower and upper parts of the triangle of the footwall are given in table. Based on the results of the calculations performed, dependencies of the angle of the caved ore flow under the inclined plane on the angle of the ore deposit dip and the distance between a draw point and the inclined surface can be built. The graphs in figure enable the conclusion that an increase in the ore deposit dip angle results in an increased angle of ore drawing under the inclined plane. Thus, an increase in the deposit dip from 45 to 60 degrees leads to increases of the angle of drawing from 57.2 to 77.2 at the distance of 10 m between a draw point and the inclined surface. When the distance between a draw point and the inclined surface increases from 10 to 20 m at the ore deposit dip of 60 degrees, the angle of ore drawing decreases from 77.2 to 68.1 degrees. Let us consider how the angle of inclination of the enclosing plane and the angle of caved ore drawing impact the draw crater radius. The calculation scheme is given in figure. Considering the right triangle ABC and knowing the width of the ore layer under breaking, the angle of inclination of the enclosing plane, the radius of the draw crater RR, triangle BCD, is determined. Thus, according to the known values from the theory of drawing caved ore under the country rocks, the radius of the draw crater is determined. The results of the calculations are given in table. As is seen in figure, an increase in the angle of plane inclination leads to the increase of the draw crater radius from 2.0 to 7.5 meters at the first loosening factor of 1.5. A decrease in the first loosening factor from 1.5 to 1.1 results in the increase of the draw crater radius from 2.0 to 7.5 meters to 4.4 to 10.0 meters. Thus, by changing the angle of plane inclination and increasing the width of the active drawing area, it is possible to reduce ore losses on the footwall. Analytical calculations of losses and dilution of ore during deposit mining using an overcompacted layer for the ore deposit dip of 60 degrees and an angle of the inclined plane of 70 degrees are given in table. Based on the results of the analytical calculations performed, dependencies of changes in losses and dilution of ore during its drawing under the overcompacted layer are built figure. As is seen in figure, an increase in the thickness of the overcompacted layer of ore decreases ore losses from 15 to 8%, and dilution increases from 6 to 16%. This is due to the fact that a decrease in the thickness of the overcompacted layer decreases the semi-minor axis of the ellipsoid of drawing, and the radius of the drawing flow under the inclined plane decreases accordingly. To minimize ore losses and dilution, it is advisable to locate the draw point in the block sill at a distance that provides formation of the 20 to 25 meters high ellipsoid of drawing. Thus, when applying the sublevel forced caving system using an overcompacted ore layer, it is possible to significantly reduce ore losses and dilution to enhance extraction of ore mass without additional costs. With the 22 meters thick overcompacted layer, ore losses and dilution can be reduced from the actual 14 and 16% to 10 and 9% respectively. The results of the studies performed enable proving that the width of the active drawing area is impacted by not only rock pressure, but also the ore deposit dip angle and the enclosing surface represented by the hanging wall or created by gradual ore breaking. Thus, losses of ore on the footwall can be reduced by changing the angle of inclination of the plane and increasing the width of the active drawing area. It is established for the first time that an increase in the thickness of the overcompacted ore layer leads to increases in the semi-minor axis of the ellipsoid of drawing and the width of the active area, which results in decreased losses and dilution of ore during its drawing from the stoping block. It is established that in order to minimize ore losses and dilution when using level mining systems, the draw point should be located in the block sill at a distance that provides formation of the 20 to 25 meters high ellipsoid of drawing. Using an overcompacted ore layer can significantly reduce ore losses and dilution and enhance extraction of ore mass without additional costs. Thus, the 22 meters thick overcompacted layer enables. Thanks for your attention.